So, we continue our lecture with characterization of fuel, and I told you about calorific value and proximate and ultimate analysis of solid fuel. Now, let us take fuel oil. As regards fuel oil, the analysis of fuel oil is given in terms of carbon, hydrogen, nitrogen, oxygen and sulfur. The calorific value of fuel oil can be easily determined from the heat of formation of various oxides, for example, carbon to CO2, H to H2O and S to SO2, and nitrogen is an incombustible component. So, all combustible components are added together with their heat of formation, that gives us the calorific value of fuel oil. Now, in general, the calorific value of fuel oil, it does not change very much. It remains in the order of magnitude of around 9000 kilocalorie per kg to around 10,000 or something kilocalorie per kg. As regard gaseous fuel, as such gaseous fuel, natural gas is the naturally occurring resource, that is, it is a fossil fuel. There are other gaseous fuels also. So, in general, all gaseous fuels have combustible component and incombustible component. And incombustible components, for example, the combustible components of any gaseous fuel that consist of carbon monoxide, hydrogen, hydrocarbons, they are the principal combustible component of any gaseous fuel. Among hydrocarbons there could be several, for example, CH4, C2H2, C2H8 or so on, all these are the combustible component. Among incombustible component we have say nitrogen, carbon dioxide, H2O. So, these are the incombustible component, or you can also call them to be diluents. That means, they dilute the energy released by combustible component. Now, the calorific value of gaseous fuel, it can be determined from heat of combustion values. Now, I am giving here typical heat of combustion values of some gases. So, I am giving here typical heat of formation values of some gases, and from heat of formation one can also determine the heat of combustion. Say for example, heat of formation of some gases, say I am giving here in minus delta H naught heat of formation, they are given at 298 Kelvin and 1 atmospheric pressure. One can put oxide minus delta H naught F, that is more correct term, minus delta H naught F, that I am giving in kilocalorie per kg mole. So, for carbon monoxide, this value is 29.6 into 10 to the power 3 when the state of carbon is amorphous. Amorphous state of carbon. In fact, the heat of formation, that is also equal to heat of combustion when carbon reacts with oxygen and forms carbon monoxide. So, in that case, heat of formation will be same as heat of combustion. CO in literature you will also find the value to be 26.4 into 10 to the power 3 when carbon is not in amorphous state. So, that point is to be clear. Similarly, carbon dioxide is 97.2 into 10 to the power 3, again here amorphous state of carbon, amorphous state of carbon, and in all other states CO2 that is equal to 94.05 into 10 to the power 3 in all other states. So, for methane the heat of formation is 17.89 into 10 to the power 3 kilocalorie per kg mole. Now, note in case of CH4 heat of formation is not equal to heat of combustion, whereas in case of CO, CO2, H2O the heat of formation will be equal to heat of combustion. So, CH4 the 17.89 into 10 to the power 3 kilocalorie per kg mole is the heat of formation when carbon reacts with hydrogen and it forms methane. C2H4, note its value is minus 12.50 into 10 to the power 3 kilocalorie per kg mole. Then C2H6, this value is 20.24 into 10 to the power 3 kilocalorie per kg mole. C3H8 value is 24.82 into 10 to the power 3 kilocalorie per kg mole. About H2O vapor and H2O liquid I had already given in my earlier lecture. Now, one more thing is important to note, that 1 kg mole of any gas, that is equal to upon 1.013 into 10 to the power 5, and that is equal to 22.4 meter cube at 1 atmosphere pressure and 273 Kelvin, whereas 1 kg mole at 298 Kelvin into 298 divided by 1.013 into 10 to the power 5, that is equal to 24.45 at 1 atmosphere and 298 Kelvin. Now, let us take an example to calculate the calorific value of say natural gas. So, I take an example of natural gas which has the composition say methane, it contains around 81 to 94%, C2H6 3 to 7%, C3H8 0.5% and rest nitrogen and CO2 they are traces. Now, how to determine the calorific value of this gaseous fuel which is in fact natural gas. Now, the first of all we have to find out the heat of combustion of CH4, C2H6 and C3H8. So, once you find out the heat of combustion of the respective combustible component of the natural gas, we can add them together and we will get the heat of combustion of natural gas. So, first of all we find out the heat of combustion of CH4. So, in order to find out say heat of combustion of CH4, heat of combustion of CH4, if we take say 1 kg mole of natural gas, then CH4 on combustion, CH4 on combustion it forms CO2 and 2H2O. then heat of combustion, of methane, that will be equal to 97.2 into 10 to the power 3 plus 2 into 57.8 into 10 to the power 3. Now, mind you, here on combustion CH4, I have taken CO2 and H2O in the vapor state. If I take in the liquid state, then I have to add latent heat of condensation. This minus heat of formation of methane, that is 17.89 into 10 to the power 3. So, if I solve, then I get the delta H combustion, that is equal to 194.91 into 10 to the power 3 kilocalorie per kg mole. Now, in fact, they are the minus value. So, this is an exothermic reaction. Similarly, we can find out the heat of combustion of C2H6. Now, C2H6 on complete combustion, it gives 2 CO2 and 3 H2O. Let us take 3 H2O as vapor. Then we can similarly find out heat of combustion, that will be 2 into 97.2 into 10 to the power 3 plus 3 into 57.8 into 10 to the power 3 minus heat of formation of C2H6 T.24 into 10 to the power 3. So, on solving, we will be getting heat of combustion, that is equal to 350.56 kilocalorie per kg mole of C2H6. Now, similarly, we can also find out another component is C3H8. So, doing same exercise, say 3 CO2 and 4 H2O are the complete products of combustion we take in the vapor state. So, again if I write down the heat of formation of CO2, heat of formation of H2O, subtract heat of formation of C3H8 as I have done, you can also do it because the values are given. So, we get heat of combustion of C3H8 that comes out to be equal to 498.18 into 10 to the power 3 kilocalorie per kg mole. Now, we have the heat of combustion values of all the combustible components. Now, note that these values belong when H2O is in the vapor state. So, we can call it to be net calorific value. So, therefore, the net calorific value of natural gas of the composition which I have given earlier, that will be equal to 0.81, taking the lower percentage of CH4, that is 0.81 into 194.91 into 10 to the power 3 plus 0.03 into 350.56 into 10 to the power 3 plus 0.005 into 498.18 into 10 to the power 3. So, this is the net calorific value of 1 kg mole of natural gas. So, to add them together, we will be getting 170.91 into 10 to the power 3 kilocalorie per kg mole of natural gas. Now, we can convert in the different units also if you wish to do that. Then NCV, that is equal to 715 into 10 to the power 3, that is kilojoule per kg mole of natural gas. We can also put that is equal to 31.94 into 10 to the power 3 kilojoule per meter cube of natural gas, mind you at 0 degree Celsius and 1 atmospheric pressure. Because when you want to express the calorific value in terms of meter cube, then you have to express what is the temperature and pressure, because the expression of meter cube, it has no meaning unless pressure and temperatures are specified. So, that is an important thing. Now, this value is also equal to 29.24 into 10 to the power 3 kilojoule per meter cube at 25 degree Celsius and 1 atmospheric pressure. So, these are this is the calorific or net calorific value of natural gas. Now, since the composition varies between 81 to 94, C2H6, 3 to 7 and so on. So, one can also determine taking other extreme composition, that is 94% of methane, 7% of C2H6, then the calorific value or net calorific value, it varies in between 170.91 into 10 to the power 3 kilocalorie per kg mole to 210.25 kilocalorie per kg mole. So, this is how the calorific value of gaseous fuel can be calculated. Now, there are some advantages of gaseous fuels. The advantages of gaseous fuels are: advantages of gaseous fuels are, say one advantage, they are clean and no ash. Gaseous fuel does not contain ash when you compare with the solid fuel, which contains 10%, 15% or 20% ash. So, in that regard, the gaseous fuel, they are clean and does not contain any ash. Another benefit of gaseous fuel is they are easy to handle. Easy to handle. Third example, good combustion can be obtained. Because one of the important condition for efficient or good combustion is the mixing of the combustible component of any fuel with the oxidizing gas, for example air. If it is good, then combustion will be good, and one can easily expect that if the fuel is a gaseous fuel, then the mixing is very good compared to when you have the solid fuel and you are combusting with the air. So, these are some of the advantages of gaseous fuels. Now, after knowing this proximate analysis, ultimate analysis and calorific value of different types of fuel, now we are in a position to classify the fuels, and we will say that the fuel which has a high calorific value, it is a good quality fuel. A fuel which has a low calorific value is relatively not a good quality fuel. So, according to this, we can classify the fuel in terms of, say, quality of the fuel and defining by way of its composition and calorific value. So, first of all, let us take the fossil solid fuels. So, I will give here some of the proximate analysis, some of the proximate and ultimate analysis of say solid fuels. Say I take here lignite, then I take bituminous coal, and then I take anthracite. So, let me first of all give proximate analysis, and all of us know proximate analysis is given of volatile matter, fixed carbon, ash and percentage moisture. Now, lignite 35.3 volatile matter, 22.9% fixed carbon, 7.2% ash and 34.6% moisture. Bituminous coal 27.1% volatile matter, 62.6% fixed carbon, 7.1% carbon and 3.2% carbon. Note the drastic decrease in the moisture as you go from lignite to bituminous coal, that is, as rank of the coal increases, the moisture content drastically decreases. Anthracite volatile matter is 1.2%, 88.2% fixed carbon, 7.8 and 2.8% volatile matter percentage moisture. Now, interesting is to write down the ultimate analysis, because if you want to find out the quality of the fuel, then we have to find out how much energy it can release, that is what is the calorific value of the fuel, and for that we need ultimate analysis. Now, ultimate analysis say all of us know is given in terms of carbon, hydrogen, nitrogen, oxygen, sulfur and ash. So, I am writing here carbon 42.4 and 84.4, hydrogen 6.6, 5.2, 1.9, nitrogen 0.6, here it is 1.2, here it is 0.6, oxygen 42.1, which drastically decreases to 7.5 and ultimately to 4.4. Sulfur, which is 1.1, slightly decreases, not very much, 0.9, and ash more or less it remains constant sort of thing. So, this is what the proximate and ultimate analysis of the fuel. Now, since we know that we can determine the calorific value of the fuel by the formula which I had developed earlier. So, we try to determine the calorific value of the fuel, and then we can say the quality of the fuel. So, if I determine the GCV of lignite, if I want to determine GCV of lignite, then you know the formula, that is 81 into 42.4 plus 341 6.6 minus 42.1 upon 8 plus 22 into 1.1. So, this comes out to be equal to 3914.6 kilocalorie per kg. Similarly, I can determine GCV of bituminous coal, and GCV of bituminous coal, again the same formula, you plug in the values of carbon, hydrogen and so on, and you will be getting the values are 7793.5 kilocalorie per kg. Similarly, I can determine now the gross calorific value of anthracite. Again I have to substitute, say 81 into 84.4 plus 341, 1.9 minus 4.4 upon 8 plus 22 into 0.9. If I solve, I will be getting 7316.55 kilocalorie per kg. So, of all the three fuels, if you want to analyze the calculation, we see that the bituminous coal has a relatively higher quality than anthracite and lignite, because the bituminous coal on combustion gives higher calorific value as compared to anthracite and to lignite. So, now as we go from lignite to anthracite, that is, if we proceed from lignite to anthracite, then our calculation suggests the follows, and also the table shows follows, that is, carbon content increases. Carbon content increases. What is the reason for increase in the carbon content? Is obvious, because the anthracite which forms it is the higher ranking of the coal, and it forms at the last stage of coalification, and because of the physico-chemical reaction, most of the volatile matters they are removed, and hence anthracite has a higher carbon content. Also you can call it to be higher rank. Another observation that you can make is that hydrogen and oxygen decreases as we go from lignite to anthracite. The reason is again in the qualification. Now, third observation that you can make, the calorific value, it increases from lignite to bituminous coal and decreases to anthracite and decreases for anthracite. Do you know why? If you see the analysis, you will find that the anthracite has a lower percentage hydrogen as compared to bituminous coal, and therefore, in the anthracite the calorific value is slightly lower than that of bituminous coal. Now, then we can also classify in the same way gaseous fuel, say classification of gaseous fuels. Classification of gaseous fuels. Now, from combustion point of view, it is the calorific value that is important. Higher is the calorific value, higher is the quality of the fuel. Lower is the calorific value, lower is the quality of the fuel. So, depending on the calorific value that a particular fuel has, one can grade in terms of quality. So, there are several types of gaseous fuels are available. I will just quote one or two example. Now, rest one you can find out from the books, you can calculate the calorific value and you can grade them. So, I am taking one example as the blast furnace gas. A typical composition which I have selected: CO2 12.6, CO 25.48, hydrogen 2.88, H2O 2.37 and nitrogen 57.21. Another gas which I am selecting is the coke oven gas. Is the coke oven gas. The coke oven gas, it has CH4 28%, CO 0.074% and hydrogen 54% and incombustible are rest. So, one can determine NCV or GCV, whichever you want to calculate. Again, you calculate the heat of combustion of various combustible component, add them together and you get the calorific value. So, for blast furnace gas on dry basis, GCV it comes out to be equal to 3671 kilojoule per meter cube, and NCV that is equal to 3614 kilojoule per meter cube, and these values are at 1 atmospheric pressure and 273 Kelvin. Now, similarly for coke oven gas, NCV that is equal to 88.5 into 10 to the power 3 kilocalorie per kg mole, and that is also equal to 16.53 into 10 to the power 3 kilojoule per meter cube at 273 Kelvin and 1 atmospheric pressure. So, this is again the NCV. So, what we can conclude from here? So, if we have 3 different types of fuels, a natural gas, blast furnace gas and coke oven gas, then as for the quality of the fuel regarding the calorific value is concerned, so one can say natural gas it has a higher quality, followed by coke oven gas and followed by blast furnace gas. So, I am just summarizing, say natural gas calorific value is 170.91 kilocalorie per kg mole. Then coke oven gas, as just now we have calculated, 88.5 into 10 to the power 3 kilocalorie per kg mole, and then we have blast furnace gas, value is 19.3 into 10 to the power 3 kilocalorie per kg mole. So, on these 3 fuel, if you are required to classify, you say natural gas is a higher quality fuel, and related to natural gas coke oven gas is lower quality, and related to coke oven gas blast furnace gas is another low quality fuel. So, if you have several fuels, one can do the classifications. Now, another important thing in case of gaseous fuel, that is gaseous fuels have range of properties. Their calorific value varies, their density also varies. So, a combustion system which is designed for one particular type of gaseous fuel is not suitable for another type of gaseous fuel. So, for this purpose a Wube index is defined. A Wube index can be defined, and a Wube index is an indicator of the interchangeability of fuel gases, say like natural gas, liquefied petroleum gas or whatever the gas may be. It is defined as the Wube index IW. It is defined always on the basis of higher heating value, higher heating value, which is also called GCV, gross calorific value, divided by square root of specific gravity. So, that is how an Wube index is defined. So, this IW in fact it compares the combustion energy output, the combustion energy output of different fuel gases, Now, in fact, either called fuel gas or gaseous fuel, they are one and the same thing. Now, if the two fuels have identical Wube index, then for given pressure and wall settings, the energy output will also be identical. That is what the concept of Wube index. So, this Wube index is commonly expressed as BTU per standard cubic feet or megajoule per standard cubic meter. Now, say some Wube index of some gases, say for example, if we have a manufactured gas, the Wube index is 22.5, varies to 30 in megajoule per standard cubic meter. For natural gas, the value is 45.5 to 55, same unit, and for liquefied petroleum gas, this is value is 73.5 to 87.5. So, all these Wube index suggest you that if you want to interchange a combustion appliance for one type of fuel to another, then this Wube index gives you a guideline. So, now I will illustrate the concepts of proximate analysis, ultimate analysis, method of expression on the different bases and the calorific value by few problems. So, first, illustration, let us take one problem, say calculate GCV and NCV of a coal which analyzes carbon 74%, hydrogen 6%, nitrogen 1%, oxygen 9%, sulfur 0.8% and moisture 2.2% and ash, that is equal to 8%. So, I require to calculate gross caloric value and net caloric value of the fuel. So, I calculate gross caloric value straight away substituting the formula. You can calculate either in kilocalorie per kg or kilojoule per kg, whichever way you want to calculate. I am calculating for kilojoule per kg, that is formula is 339 into percentage carbon plus 1427 percentage hydrogen minus percentage O upon 8 plus 22 percentage sulfur, this value you will get in kilojoule per kg. So, I will be just substituting the value 339 into 74 plus 1427 6 minus 9 upon 8 plus 22 into percent 0.8. Now, all that you have to multiply and add them together. So, the values will be 32060.2 kilojoule per kg. This is how you will be calculating. Now, similarly, the NCV, net caloric value, there the state of products of combustion is vapor of water, then the net caloric value that is equal to GCV minus 24.44 9% H plus percentage moisture. So, if you do that, if you substitute the value of percent H, that is equal to 6, moisture is 2.2, substitute, you will be getting 30,630 kilojoule per kg. So, this is the answer, this is the answer. Now, one of the important is to analyze the answer. Now, if you note from here, you see that NCV is equal to 0.955 times gross calorific value in this particular case. Why it is so? Because net calorific value considers H2O in the vapor phase, and this is very important from combustion point of view, because the heat of vaporization of water will not be available for the heating of product in a furnace. So, it depends on the situation where gross caloric value is to be calculated and net caloric value is to be calculated. Now, once again, in the gross caloric value, the state of H2O is liquid, in NCV the state of water is vapor. So, that is why the difference is there, and the net caloric value is 95.5% of that of gross caloric value. Now, let me take another problem. Say the ultimate analysis of coal is given. They are given ultimate analysis, it is given on moist basis. Given on moist basis, say carbon 69.8, carbon 69.8, hydrogen 4.6, nitrogen 1.4, oxygen 8.5%, well they are all in percentage, percent. Sulfur 2.5%, moisture 4.5% and ash is 8.7%. Now, the gross calorific value is determined from experiment, and gross calorific value is found to be 29,920 kilojoule per kg. Now, you are required to find GCV from Dulong formula as I given earlier and compare the values, and you have to find out the value of gross caloric value on moist basis. So, all that you have to substitute the composition as it is given, and the value the answer which you will be getting in this case, that will be around 28,765.2 kilojoule per kg. So, therefore, your observation would be the Dulong formula calculates 0.96 times that of experimental one. Now, let us take the third problem. You have been given a coal of the following composition. Say coal, the following composition, it has moisture 2.4%, volatile matter 29.4%, fixed carbon 58% and ash 9.7%, sulfur 0.5%, GCV is given 320.23 kilojoule per kg on moisture free basis. Moisture free basis. Now, what you are required? You are required to calculate. So, calculate proximate analysis and calorific value on dry basis, and also calculate the proximate analysis and calorific value on dry ash free basis. So, you calculate it. I am giving you the answer. The answer for 1, that is equal to 32,810 kilojoule per kg, that is for the 1, and for the second the answer is 36,431 kilojoule per kg. So, that is what the answers. Now, let us take another problem to illustrate further the concept that are involving the calorific value. Now, in the fourth problem, what I have done, say ultimate analysis is given on dry basis. Now, analysis is say carbon 77%, hydrogen 5.8%, nitrogen 1%, oxygen 4.8%, sulfur 2.4% and ash, that is equal to 9%. Now, it is also said that the moisture content of the coal, is 5%. GCV of this coal is 32020 kilojoule per kg on dry basis. What you have to do now? So, you are required to calculate. So, calculate a GCV on moist basis. GCV on moist basis, B NCV on moist basis, C NCV on dry basis, and D GCV dry basis through Dulong formula. Now, in this particular problem, the analysis is given to you on dry basis. So, the analysis it becomes 100 on dry basis and moisture is given to you separately. So, now you have to calculate gross caloric value on moist basis. So, first of all, this analysis from dry basis is to be converted on moist basis and then you can proceed for the calculation. So, I just calculate, I give you a hint for calculation, say for dry basis, the analysis say carbon, hydrogen, nitrogen, oxygen, sulfur and ash 77%, 5.8%, 1.0%, 4.8%, 2.4% and 9%, and if you can add them together it becomes 100%. So, moisture is given as 5%. So, on this composition you cannot calculate the gross caloric value on moist basis. So, first of all, this composition has to be converted to moist basis. So, how would you convert on the moist basis? So, if you convert this on a moist basis, then the moisture content, it contains hydrogen and oxygen. So, you have to find out the H in H2O and O in H2O and subtract the respective H and O values, and then you get the value on the moist basis. So, if you do that, we have say carbon 73.2%, hydrogen 5.5%, nitrogen 0.95%, oxygen 4.55%, sulfur 2.30%, ash 8.5% and moisture is equal to 5%. Now, it adds to 100%. Now, you can use the formula which I have given to you earlier. So, if you use the formula, I am straight away giving the answer. So, GCV on moist basis, that is equal to 31,804 kilojoule per kg. Then NCV on moist basis 30,472.2 kilojoule per kg. Then NCV on dry basis, that comes out to be equal to 32,076 kilojoule per kg, and GCV on dry basis by Dulong formula, that is equal to 33,473.2 kilojoule per kg. These are the answers for the question which I have just given to you. Now, the last question that I will give you, that you can solve yourself, you have to find out the net calorific value. Say find net calorific value of producer gas of composition: nitrogen 50%, CO 25%, hydrogen 19%, CO2 5%, O2 1%, and the answers for this problem would be the NCV. You have to calculate the NCV of producer gas, and that will be equal to 5210 kilojoule per meter cube at 273 Kelvin and 180 m. This is the answer for NCV. Now, you can also calculate GCV, and the answer for GCV, that is equal to 5584 kilojoule per meter cube, 273 Kelvin and 1 atmospheric pressure. Think why GCV is greater than NCV? Because here the state of product of combustion is liquid. Thank you.